This is day 8 of Unit 4. Today we did not have a warm-up. We started right away with the lesson. And today we are going to be talking about imaginary numbers. So let's take a look at this first problem. So looking at that, I can see that there's no x, so I'm immediately thinking square roots technique. So let me subtract 1 so that I can use the square roots technique. So square root, take the square root of each side. We know on the left the square root of x squared is the absolute value of x. On the right, you've been told all through your math classes in the past you can't do that, or it's not real, or something like that. Today we're going to talk about how to simplify that. For right now, I'm just going to leave it as the square root of -1. So then x is equal to plus or minus, and again we'll leave that for right now as the square root of -1. Okay, so next thing I talked about in class is I actually read a little story, which I'm going to read here as well. But it basically just kind of describes what imaginary numbers are and how they came about. So it says, mathematicians throughout history have resisted the notion that some equations were not solvable. Still, it made sense that x squared plus 1 equals 0 was not solvable, which is what we're solving right now, was not solvable or didn't have a solution. Because when we solve that, we're getting the square root of -1. And that's not possible. Also, if you think about the graph, y equals x squared plus 1, we know that's a parabola that's been shifted up 1. Okay, the solutions when we solve quadratic equations, the solutions are where the parabola crosses the x-axis, or in other words, the x-intercepts. So if I'm graphing this, if this is the graph for this equation, it doesn't cross the x-axis. So that makes sense that it shouldn't have any solutions because it doesn't have any x-intercepts. Okay, so that seems to make sense, and that's what all along you've been told. However, in some ways, each person's math education parallels the history of mathematical discovery. When you were much younger, if you were asked, how many times does 3 go into 8? Or what is 8 divided by 3? You might have said 3 doesn't go into 8. Then you learned about numbers other than whole numbers, and the question had an answer. Later, if you were asked, what number squared makes 5? You might have said no number squared makes 5. Then you learned about numbers other than rational numbers, and you could answer that question. Similarly, until about 500 years ago, the answer to the question, what number squared makes -1, which is what we're doing right now, what number squared makes -1, was no number squared makes -1. Then something remarkable happened. An Italian mathematician named Bombelli used a formula for finding the roots of third-degree polynomials. Within the formula was a square root, and when he applied the formula to a particular equation, the number under the square root came out negative. Instead of giving up, he got a brilliant idea. He knew the equation had a solution, so he decided to see what would happen if he pretended that there was a number you could square to make a negative. Remarkably, he was able to continue the calculation, and eventually the, quote, imaginary number disappeared from the solution. More importantly, the resulting answer worked. It solved the equation he had begun with. This led to the acceptance of these so-called imaginary numbers. Though the name stuck, and mathematicians came to believe that equations like the one above do have solutions. Okay, so that's the little story. So the point is, when you didn't know a whole lot about numbers, when you were just learning, you started off, the very first thing you probably learned was how to count. Okay, and so we know those are the counting numbers, or we know they're called natural numbers. Then you learned a little bit more, and you learned about 0 being a number. And then you learned a little bit more, and you learned about negatives. And then you learned a little bit more, and you learned about decimals and fractions. And then you learned a little bit more, and you learned about rational numbers, square roots, and irrational numbers. And so as you were learning more about different types of numbers, the set of real numbers expanded for you. So you started off just with those counting numbers, and then you kept learning about more and more numbers. And then things that you weren't able to do previously, like tell me what 8 divided by 3 was. You know, when you first were learning about numbers, you said you can't divide 8 by 3. But eventually, once you learn more about numbers, that had an answer. So as you learn more and more about different types of numbers, and you knew basically your set of real numbers kept expanding, you were able to answer questions that you couldn't answer previously. And that's really how imaginary numbers work as well. So remember, the first day of school, beginning of the year, we looked at that big set of real numbers. Okay, and remember, we split it up between rational and irrational. Okay, and then we talked about all those subsets, and I'm not going to go through this whole set again, but remember, we talked about the natural numbers. Okay, and again, so forth. Then we talked about whole numbers and rational numbers. And we talked about irrational numbers. Well, the point is that now we need to talk about more than just the real numbers, because there are these other numbers that are not anywhere on this, that are nowhere in this set. Okay, nowhere in the set of real numbers are these numbers that Bombelli discovered called imaginary numbers. Okay, so they're off to the side. Okay, so when you hear the term imaginary numbers, what I don't want you to think is that they don't exist. The term imaginary is kind of a tricky term. Imaginary, we think like unicorns and things that don't exist. Fantasy. It's not, they're not imaginary because they don't exist or it's a fantasy. They're imaginary because they're not part of the set of numbers that we currently know called the real numbers. Okay, so if they're not real, and when I say not real, I don't mean don't exist. But when I say not real, I mean not part of the real number set. So if they're not real, then they're imaginary numbers. Okay, they do exist. It's just that they're not part of the set of real numbers. So what Bombelli did was he was trying to solve this really complex equation. Not this one we're trying to solve here, but a really complex equation. And he didn't want to give up. And he said, okay, well, I'm going to, for right now, I'm just going to call, anytime I see a square root of a -1, I'm going to call it I. Okay, so you want to add that to your notes. The square root of -1 equals I. So he substituted in, every time he had square root of a negative number, he put I in its place. And what eventually happened, if you were listening to the story, what eventually happened was the i's went out of the problem. Because when you simplify, especially when you're taking I to an even power, we'll see that in a little bit here, the I actually goes away. And then you're back to just the set of real numbers. Okay, so that's what happened when he replaced square root of a -1 with I. So back to our problem, in order to solve this, we're going to say that x is equal to plus or minus I, and those are our two solutions. Okay. Now, the other thing that we need to know is that when we take I and square it, that equals, think about this, if I square both sides, that equals -1. So back to our equation here, if I substitute I in place of x and I square it, I know that that equals -1. So when I add -1 plus 1, I do get 0. On the other hand, when I put -1 or negative I in and square it, -I times -I is positive I squared, and positive I squared is -1. So once again, -1 plus 1 is equal to 0. So we are getting, we're showing that those solutions, even though they're not part of the real number set, they're called imaginary numbers, they do solve this equation. Okay, so the equation does have solutions. It's just they're numbers that are not part of the set of real numbers. They're imaginary. Okay, so today, that's about all we're going to talk about in terms of why or the importance of imaginary numbers. We'll talk about that more in the next several lessons. But the rest of today's class is really just going to be looking at some of the basics for simplifying using imaginary numbers. So, square root of -4, if I want to simplify that, I'm going to rewrite that as the square root of 4 times the square root of -1. Now, that's going to help me because I can simplify the square root of 4, that's 2, and now I know that the square root of negative 1 is I, so the square root of negative 4 is equal to 2I. Okay, similarly, I'm going to do the same thing here. Think about that a moment. That's going to equal 4I. Okay, you don't have to show the work there. I was just showing that to explain, but that's going to be 4I. Here, 8's not a perfect square, but I can simplify root 8 to 2 root 2, and then there's an I, so 2I square root 2 is the simplified form of the square root of negative 8. Notice when I write the I make it look cursive, and the reason we do that is so that we know that I is a number, part is an imaginary number, and not I is representing a variable. Also, we in math try not to use I as a variable, but you should make it look cursive. That way it's clear that we're talking about the imaginary number I and not a variable I. Next one, square root of negative 12. We're going to simplify that to 2 root 3. And we have I because of the negative. So 2I, the square root of 3, is the simplified form of square root of negative 12. Next, so these are all possible to simplify as well. And remember, the negative really just makes I. So I have the square root of 4 over the square root of 25 I. Now, notice there's only one I, and that's because the square root of negative 4/25 is really the square root of 4/25 times the square root of negative 1. There's only one square root of negative 1, which means there's only one I. A lot of times students will think that there's an I in the numerator and the denominator. There's just one I. There's just one I because there's just one square root of negative 1. So then I'm going to simplify further, and that's 2/5 I, which I can write it exactly like that, or if I want to, I can put I in the numerator. Don't put I in the denominator, though, either in the numerator or off to the side. So this one, root 2 over 3I. Next, root 1 over root 8I, which I can multiply by root 8 over root 8, which is root 8 over 8I, which is 2 root 2 over 8I. And 2/8 simplifies to 1/4, so that's root 2 over 4I. Next, this is root 2 over root 15I times root 15 over root 15 gives me root 30 over 15I. Next. So we're going to multiply these just like they were variables. If I said what's 2x times 3x, you'd say 6x squared. So 2I times 3I is 6I squared. So that's no different than what you're used to. At this point, though, it does become different because we know that I squared, if you recall from a couple minutes ago, I squared equals negative 1. So I'm going to replace I squared with negative 1, and 6 times negative 1 is negative 6. So what just happened here was we started with imaginary numbers, but when we squared imaginary numbers, we ended up getting just a real number. So that's very similar to what happened with Bombelli when he used I as a substitute into his really complex equation. He ended up squaring I, or taking I to an even power, and the i's dropped out, and then he was just left with real number solutions. So that'll sometimes happen. You'll have imaginary numbers to begin with, but you'll end up with just a real number. So let's look at this one. 2I, the quantity squared, we know that's 4I squared times negative 5I. And 4I squared we know is 4 times negative 1, which is negative 4. And we're going to multiply that times negative 5I. So negative 4 times negative 5 is positive 20I. 20I is the solution. Next, 3I, the quantity cubed. I'm going to cube 3 to get 27. I'm going to cube I to get I cubed. Now, you cannot leave, it's considered not simplified, if you have I squared, I cubed, I to the fourth, and so forth. You can leave I in your answer, like in the last one, or just a real number answer, but you can't have something that's I squared, I cubed, I to the fourth, so forth. So I need to simplify that. So let's think about how to do that. I cubed is the same thing as I squared times I. Well, the reason I broke it down that way is because I know what I squared equals. So I squared is negative 1 times I times 27 gives me negative 27I. Next, we want to simplify I to the 28th. Well, we have to think about how we're going to do that. So we just did I cubed, we did I squared. So I'm going to write I cubed here. I'm going to add that to our list. I cubed, remember, was I squared times I, which is negative 1 times I, which is negative I. We're going to add a few more to our list. So I to the first power, that's just I, right? That's what we had in this one here. We had I to the first. I to the 0, anytime you have a number except for 0 to the 0 power, that always equals 1. So those 4 are the values that you have to know. And the reason you don't have to know any others is because if I try and do I to the fourth, that's just I squared times I squared. Okay, well, that's negative 1 times negative 1, which is 1. I to the fifth is I to the fourth times I. Well, I to the fourth was 1, and 1 times I is I. Okay, and after looking at a few of these, hopefully you're starting to realize there's a pattern here. We start with 1, then I, then negative 1, then negative I. Then we go back to 1, then I. If I continued, it would be negative 1, and then negative I. And then if I continued, it'd be 1, and then I, and then negative 1, and negative I. So the pattern is it's going to be one of these 4 options, either 1, I, negative 1, or negative I. So if I'm trying to figure out what I to the 28th equals, I know it's going to be one of these 4. So I'll take that exponent of 28 and I'll divide by 4 to see how many times 4 goes in, since there's 4 different options for what it could equal. So when I do that, I'm getting obviously 7. And I don't actually care about the 7. 7 only really tells me that we go through this cycle of 4 different options. We go through that 4 times. Or 7 times, sorry, because we got 7. So 7 times 4 is 28. Now, what I more care about, rather than just the fact it goes through the cycle 7 times, I care more about where it stops in the cycle after it goes through 7 times. And that number is the remainder. So after going through the cycle of 4 options 7 times, it stops in the next cycle. It stops at I to the 0. Okay, I know that because the remainder is 0. So that means I to the 28th is the same thing as I to the 0, which we know is 1. So I to the 28th is 1. So that's what we'll do with 29. So obviously we're going to still divide by 4. We're still going to get 7. We're still going to get 28. But this time our remainder is 1. So that means that after 7 times through the cycle, 4 different options, it's going to stop at I to the 1, which means I to the 29th is equal to I to the 1, which is equal to I. And that's how you do those. Next, let's try these. So we're going to simplify, and again, you're going to think of these i's like they're variables. So if they were variables, I would combine like terms, which is exactly what I'm going to do. 2 minus 6 is negative 4, and 3i minus 4i is negative I. That is my answer. That answer, by the way, is called a complex number. Complex numbers have both a real part and an imaginary part. Okay, they have a real part and an imaginary part. So in our example here, in this answer, we had a real part, negative 4, and we had an imaginary part, negative 1i. When you put those two together, and you can't combine them because they're not like terms, but when you put those two together, we call that whole thing, negative 4 minus I, we call that a complex number. So we're going to try a few more here. Now this time I have two binomials. There's no sign in between, which I know means I'm going to be multiplying them. So I'm going to set up a generic rectangle, 2 plus 3i and 6 plus 4i. And I'm going to multiply 6 times 2 is 12, 6 times 3i is 18i, 4i times 2 is 8i, and 4i times 3i is 12i squared. I'm going to combine like terms, so I have 12. I have 8i and 18i, which is 26i, and I have 12i squared, which I can simplify. We know 12 times negative 1 is negative 12. So I'm going to now combine the 12 and the negative 12, because they're like terms, which they're going to cancel out, and I'm going to be left with just 26i. And that is my solution. Next, we'll try this one. Again, we're multiplying binomials. So I have 6 minus 2i and 3 plus 5i. So we have 3 times 6 is 18, 3 times negative 2i is negative 6i, 5i times 6 is 30i, 5i times negative 2i is negative 10i squared. So I have 18, negative 6i and 30i is 24i. And negative 10i squared means negative 10 times negative 1, which is positive 10. So I'm adding 10 on. So 18 plus 10 is 28 plus 24i. Oops, that's a weird 2, 24i. So 20, I'll write that again. 28 plus 24i is my final answer, which you can see is a complex number. By the way, when we write complex numbers, we write the real part first and the imaginary part second. So 28 plus 24i is the proper way to write it, rather than 24i plus 28. The real part comes first. Next, let's try a few more. So if I simplify 5 plus the square root of negative 6, I'm going to write 5 plus I times the square root of 6. Next, negative 18 minus the square root of negative 25. Well, square root of negative 25 is 5i. So negative 18 minus 5i. And that doesn't simplify because that's a complex number with the real part first and the imaginary part second. Here, these last two look like solutions we would get when we're solving using the quadratic formula. And remember, you were told at one point to just stop there because you couldn't go any further. Well, now you can, because now you know how to simplify imaginary numbers. So square root of negative 16 we know is 4i. I'm going to simplify that further. I see a GCF of 2 in the numerator, so 1 plus or minus 2i. And now that I've factored out that 2, I see 2/10, which simplifies to 1/5. So I have 1 plus or minus 2i, and that's all over 5. Next one, we're going to simplify that square root of negative 27, which simplifies to 3i root 3. Next, we're going to simplify the GCF, factor it out, 3 times 1 plus or minus I root 3. And that's all over 9. And then 3/9 simplifies to 1/3. So I'm getting 1 plus or minus I root 3 all over 3. And those are my final answers. So homework for tonight, pages 17 and 18. Remember, stay on top of your assignments. We're getting into the difficult material here. Don't want to fall behind. Pages 17 and 18, do those for tomorrow.